library because I love knowledge. Use your medulla oblongata and give me scoliosis until I comatosis and do it while I sleep. Yeah, a little osmosis. Oh shoot. We're recording. Hi, sorry. This is chapter 11, Holes Anatomy. This is part 3, Meninges and Spinal Cord. Let's chat. We have the CNS here. We're looking in at CNS under the scalp. And here you see the skull and the vertebral column. That makes up the CNS. And then we're talking about the meninges here. So part of the meninges, or within there, you see the CSF, or cerebrospinal fluid, that flows here through the around the arachnoid mater layer, just below the dura mater. And here we also have the blood-brain barrier, that is from these blood vessels that go that pierce through the pia mater, the closest, and enter into the brain and provide nutrients and so on. So let's talk about these specific meninges. The dura mater stands for tough mother, and it's the outer covering. It's continuous with the skull itself. The periosteum, it's attached to the surface of the skull, and then the meningeal layer is the outer covering of the brain. So there's the double layer, external covering of the brain for protection. You'll see when we do our dissection, my brain hurts, that the dura mater is quite hard and tough. It's for protection. The arachnoid layer is web-like. It's named after a spider. It's more like a loose sac around the brain that the brain is sitting in. And there's also some blood vessels that you'll see just beneath this arachnoid layer. And finally, the pia mater, we have tight to the brain, suction to it, and it goes in with all the gyri and sulci, and it clings to the surface. It's the most internal, most delicate layer of all the meninges. All of them, including the CSF, serve to protect and to nourish the brain. Here's the CSF, cerebrospinal fluid, similar to the blood plasma. It's formed by the choroid plexus, specifically ependymal cells in the choroid plexus, and it's a cushion for the brain, so that when I do this, my brain doesn't bang into the side of my skull and cause a concussion, cause me harm. At least that's what it's supposed to do. As I mentioned, the arachnoid space has CSF as well as the various ventricles, 1, 2, 3, 4, and then the central canal that runs down the middle of the spinal cord also carries CSF. Here we have the ventricles. You see the lateral ventricles on either side here. Those are the major ones that you see looking black in scans of a brain. Those are the lateral ventricles. The third ventricle is right in the middle, and then we have a cerebral aqueduct that runs to the fourth ventricle, and finally the central canal that runs down the spinal cord. And here you see how it circulates, how it's created by the choroid plexus. There's a couple of them here that create it, and then it circulates around and around and around, and then down through, and then back up. So the brain and spinal cord are basically floating. They're not physically touching any of the surroundings for protection. Now, the blood-brain barrier, what cell again? Oh, yeah, ependymal cells. These are the least permeable capillaries of the body, meaning things have a very difficult time getting through, including harmful substances. Now, sometimes some things can get through, such as fatty and fat-soluble molecules have a better time getting through. And then very teeny tiny things like respiratory gases. Alcohol is very small. It's able to pass through and thus affect the brain. Nicotine, drugs used for anesthesia, all those pass across the blood-brain barrier. Now that I think about it, I said what cell forms the blood-brain barrier? It's astrocytes. It's not ependymal cells. Those form CSF. So I misspoke earlier. Sorry about that. Here we have nicotine anesthesia getting across the blood-brain barrier and having an effect on the neurotransmitter levels in your brain, and thus stimulating or depressing certain regions. Now into injuries, traumatic brain injuries. So concussion, when your brain bangs into the side of the skull, that's called a concussion. It's a slight brain injury. You can have a mild concussion or a severe concussion, a full concussion. The more concussions you have throughout life, the more the damage builds up. Cells die and you begin to lose function over time. And you see all these football players going through these issues now as they get older because of so many hits to the head, and now there's lawsuits and things being filed on them and at the football leagues. We will investigate this further next week. A contusion is when nervous tissue is actually cut. Now, you can have a contusion of the skin as well. Contusion just means cut. But with nervous tissue, when the destruction occurs, you cannot regenerate those cells. They stay cut forever. Neurons do not regenerate, as you know. And then cerebral edema is when you have a buildup of fluid in the or on the top of the cerebrum, so it's swelling. And this can cause pressure against the brain and under the skull because there's only so much room that's available. So, for example, one of the treatments that still occurs and has occurred for hundreds and hundreds of years is to create a little hole in the skull and allow some of the fluid to leak out to alleviate the pressure. Sometimes now, if the brain is swelling, they may even remove a portion of the skull. I saw a thing about a snowboarder, professional snowboarder, who had a head trauma, and they took off a portion of his skull and they actually surgically implanted it into his abdomen to nourish the bone, while they left his brain open to the air to swell to minimize the pressure. And then when the brain went back down, they put the skull piece back on from his stomach. Crazy stuff. And he survived and recovered and so on. CVA, or cerebrovascular accident, you may know that better as a stroke. When a blood vessel ruptures, or a blockage occurs and some cells on the other end die. It's like a heart attack of the brain, okay? Oxygen is lacking, and then those cells are going to die. You're going to have to retrain your brain to have other new areas perform functions that were lost. And this takes time. Often people can recover completely or very close to completely by training new brain areas to learn. This is called plasticity. The brain has plasticity. It can learn new things. As long as the stroke doesn't happen in regions that are for certain autonomic processes that you can't really relearn or redo. Alzheimer's disease, as you mentioned, progressive degenerative brain disease, you can't do anything to prevent it. Mostly seen in the elderly. It can begin, typically begins in your 40s or 50s, maybe later 50s, 60s. It's a form of dementia, and they forget, as you know, many, many things. And what you find is that there are protein deposits in the brain, these plaques that form, and then the fibers themselves start to look abnormally shaped. The neurons themselves around the fibers around the neurons start to look like they're not supporting the neurons properly, and these plaques and so on build up and cause the brain to not function. So memory loss. Typically, they're irritable because of their inability to function properly. At least that's the current thought. And then they might be confused and potentially in the end cause death if there's enough degeneration. Okay, on to the spinal cord. Here we see the spinal cord, cervical, thoracic, and lumbar at the bottom. There's 31 pairs of spinal nerves that come off at each junction where the vertebrae are, where there's space. And you'll also notice where the upper limbs and the lower limbs are, there's these bulges because there's lots and lots of peripheral nerves coming off in those regions. Below T12, down here, we have what's called the cauda equina, which is not part of the spinal cord anymore. This is down into the lumbar region. It's a collection of spinal nerves that all already start to branch in this lumbar region, and it actually stands for horse's tail, and it looks like that. So spinal cord has ascending and descending tracts. It's communication to and away from the brain. The meninges wrap around it just like in the brain for protection. And as I mentioned, the enlargements, here you see cervical enlargement and lumbar enlargement. Serving the upper and lower limbs, there's more things that branch out to those limbs. Now here you see a cutaway view of the spinal cord. It always looks kind of like a butterfly. And here's the central canal that we mentioned previously. And here's those peripheral nerves that are emanating out and merging to form one spinal nerve on either side. Now there's some different terminology here that you have to know. Things called horns. These are regions that stick out. Horn, horn, horn. And they're named based on the side of the body that they're on. So this is the dorsal side, or we call this posterior horn or dorsal horn. And these are all interneurons in there. Okay, and this is of the gray matter. It looks a little brown, but this is the gray matter. On the outside is the white matter. Then you have the ventral horn or anterior horn. These are all, as you see here, these are all motor neurons. So the motor neurons are going to go from here and connect out through this pathway, this branch, as you can see here. And then you have lateral horns, as you can see there, which are the cell bodies of those motor neurons that are going to connect. You might see here a ganglion. You notice gray matter outside the central nervous system. These are, you have ganglia. Here's the dorsal root ganglion, because this is on the dorsal side okay, in the root of the neuron. And I think you see the dura mater on the outside, the arachnoid mater next to it. It's like the baggie. And then close up, which you can't even really see, attached to the spinal cord, is the pia mater. We already mentioned the meninges. Nerves leave at each vertebrate level. The dorsal root, so there's dorsal root ganglia. These are collections of cell bodies outside, as I said. And the ventral root and dorsal root meet up to form that spinal nerve that's then going to go out. And that spinal nerve, as you know, has pathways that go both directions, both motor and sensory components. Whereas, if you can see here, as we said, the anterior ventral has motor. So this side is going to be your motor neurons going out, and this side is going to be your sensory neurons coming in. So this whole side of the spinal cord is basically ascending tracts, and this side of the spinal cord is going to be descending tracts. So that information is going to go certain ways. So you might imagine if you have damage to only certain parts of the spinal cord or compressions, let's say on this part of the spinal cord, it's going to affect sensation, but not motor function. So now you see white matter outside the gray matter, okay? And these are conduction tracts, as I mentioned. They're myelinated. The posterior column has ascending tracts that you see here. So we said those are sensory. And then the anterior and lateral columns, those are on the sides and over here. These are both ascending but also descending, your motor pathways taking the information out. And then the central canal filled with CSF. Now, receptors in your skin. There was no real good place to put this, so I just kind of put this into here. Different types. There's mechanoreceptors, which respond to touch and pressure. Ow, that doesn't hurt. Ow, that hurts. I actually did really hurt myself. Chemoreceptors, which sense chemicals. Now, there's a lot of these that I'm not mentioning because they're in our senses unit. Chemoreceptors you would have like in taste and smell. And then thermoreceptors are temperature. Okay, so of the mechanoreceptors, some of them you've seen before, but Pacinian corpuscles are deep pressure. So when you push, you can feel that's different than just a light touch, like a fly landing on you, which is Meissner's corpuscles, different type of nerve ending. You have muscle spindles, as I hopefully mentioned before, but muscle spindles wrap around myofibers, and when the myofiber contracts, it sends a message because that spindle stretches or moves, and it's connected to your nervous system up to the brain, and that helps you to give you information about where you are or balance, which muscles are contracting, and so on. Golgi tendon organs perform similar functions, but they're wrapped around the tendons, the tendon portion of the muscle. They're also for proprioception, and these, for example, in the knee-jerk reflex, these change shape because of the stretch caused by the hammer, and that sends messages to your brain also, Golgi tendon organs. Mechanoreceptors, you also have nociceptors, so pain caused from pressure or mechanical damage. That's just pain from trauma. Chemoreceptors, pain from chemicals, so whether, for example, capsaicin is the chemical in spicy peppers, and if you eat spicy peppers, that can cause pain. Those are nociceptors. So nociceptors, you'll see multiple types of receptors are nociceptors. And then lastly, thermoreceptors, these are temperature. When it's really cold, you feel through the cold receptors. They're a type of free nerve ending. Warm receptors are in the dermis, where cold receptors in the epidermis, so cold is a little easier to feel than warm. Warm receptors in the dermis, these feel temps 32 to 48, so normal warm temperatures up into the low 100s, basically, or to the mid 100s. And then beyond that, when it's very cold or very hot, you actually can't distinguish between the two. So if you have ice on your skin, it can cause a burn because it's very, very hot or painful. I actually had a friend in high school who was a pitcher, and I remember coming home after one of his games one day, and he put ice directly on his shoulder. Half an hour later, he took the ice off. He had a second-degree burn. I mentioned that previously in a different unit. But that's because the ice was very, very hot. Dry ice is very, very cold, but it's the same thing, hot and cold. You can't tell the difference between the two. They just activate nociceptors. You almost don't feel that they're cold or hot anymore. And lastly, let's just talk briefly about the structure of a nerve. You'll see this is very similar to the structure of a muscle cell. Okay, we have a wrapping around each fiber called the endoneurium, just like we saw in myofibrils. Here we have a neuron, and we have the myelin sheath and an axon and so on. The endoneurium wraps one around that. It's connective tissue. And then those neurons are grouped together into a fascicle. Here we see a fascicle, and that fascicle is wrapped in perineurium, okay? Also connective tissue. And then lastly, you have the epineurium, which binds all the fascicles together into your actual nerve itself. So this is one nerve made up of many, many neurons. And you notice, based on each fascicle, that one fascicle might be an ascending pathway, and one fascicle, I pointed to the left, an ascending pathway, one fascicle might be a descending pathway, taking information multiple directions. And again, the more neurons that send the same message at the same time, that arrives at the same location, the stronger that sensation is. And we are done. On that note, I am going to bid you adieu.